All right, so we're doing internal loads and beams. And we started talking about distributed loads. We did one example at the end of last time, and now I'm going to show how we deal with weight with internal loads. When you're doing internal loads problems, weight has to be treated as a distributed load. It's hard to write with my arms shaking so much from exhaustion. No, just in class. But that was the most handstand practice I've had in many years. So, I'm sure I will. So weight has to be treated as a distributed load. But when you do distributed loads, to do the calculation, you have to represent them as a point force. So that whole thing is a little confusing. Point force. Huh? Yeah, that was good. So what's the deal? You know what I mean? Like, is it a distributed load or a point force? This is the key. The key thing is you can't treat a distributed load as a point force until you've chosen the body to isolate. Okay, so I'm going to do an example with weight. Yep. Because what? Yeah, it's the key thing is St. Venant's principle is important when you have one loading pattern and you're trying to replace it with an equipolant loading pattern. When we're dealing with beams, we're assuming that the mathematical way that we're representing the loading is the actual way that it's loaded. Okay, so we never have to make that substitution. It's the substitution that messes things up near the loads. Yeah. Yeah, so you only have to worry about St. Venant's principle if the loading pattern that you're dealing with mathematically is not exactly the same as the loading pattern that is really going on. So like remember, let me draw a picture of this. It's right. So if you well, okay, so you might have a setup like this where you have a cable attached to the two ends of this bar and you're applying forces like that. Okay. Mathematically, we don't know how to do this calculation. We do know how to do this, where we have a bar with the same cross-sectional area and we have uniform distributed loads at the ends that come to a magnitude, a total force F, okay? We don't know how to do this one. We do know how to do this one. So mathematically, we're going to replace what's really happening at the ends with these uniform distributed loads. Once we make that replacement, we have to be careful not to trust our values close to where those forces are applied. Yeah, but when we're doing these beam problems, we're not making any substitutions. We're assuming that the distributed loads are the ones that we're treating them as. Anything that is a point force, we're treating as a point force, so we don't have to worry about that. Yeah, that's right. Although, yeah, well, let's. I should probably think about that more. But there are times when weird things happen at the ends. There are times, but I think overall you can think about this as St. Venant's principle isn't really a deal with this. Okay, so the example. So let's say that we have a 2-meter long bar that's cantilevered at the right end. And the mass of the bar is 100 kilograms. And we want to calculate the internal loads. Normally, the first step would be to calculate the external loads. We don't have to do that here because the only unknown external loads that we would be calculating are at the far right end, and so that's never going to come up in our internal loads calculations. So we can skip the external loads calculation. Whenever the unknown reactions are at the right end of the beam. Right. Then we have to do it, yeah. That's right, because, and the reason is that we always work from the extreme left towards the right. And, yeah. Okay, so how many places, well, let me draw a free body diagram of the whole thing. Let's see what's going on. We have a total weight force of 100 times 9.81, right? So 981 is the total force. And that's distributed over 2 meters. So we have a distributed force that's 981 divided by 2 meters. Which is 490.5 this per meter. Okay, and that makes sense because if you want to calculate then the total force produced by this distributed load, you think of that as a rectangle with a height of 490.5 and a width of 2, and the total force is the area of that rectangle, which is 490.5 times 2. And then we have the reactions at the right end. That's a reaction force. I'll call that R. A couple MR. And generally speaking, a torque, although there's no torques in this problem. I'll call that TR, reaction torque. Yep. That's right. So we're normally, we would solve for these unknown reactions, but in this problem we don't have to because they're right. Okay, so now I just drew this free body diagram so we could think about how many cuts we need to make. So there's going to be a cut between the endpoints. Are there any other places besides the endpoints where we have point loads or distributed load functions change? Nope. So n equals 2. And that means that we're just going to do one cut, n minus 1. So cut 1 is valid for all x's between 0 and 2. So here's the piece we're isolating, and here's the piece that we're not isolating. There's all this stuff going on over here. But the part we care about is what's happening to our isolated piece. This distributed load has a magnitude of 490.5 newtons per meter. And then we have internal loads, the tension, shear force, bending moment, and torque. And the length of this piece is x. Okay, so now we have committed to piece to isolate. Okay, we got it down on paper. We can't change it now. So now that we've chosen the piece to isolate, now we can represent it that distributed load as a point force. No, we don't. That x value could be anything between 0 and 2. Okay, so it could be. So this represents everything from a tiny little piece of this beam to a piece that's almost all the way to the end. Okay, any value of x. And so we're calculating everything as functions of x. So now we've chosen the body to isolate. And that means we can represent that distributed load as a point force. So I'll draw this again. The free body diagram. So here is the piece we're isolating. That distributed load, let me do the other things first. So here are the internal loads. We got T, V, M, and torque. And now we want to represent that distributed load as a point force. That's a rectangular distributed load. So it has a height of 490.5, a width of 2. So the total force is 2 times 490.5. Yes. X. So the area is 490.5 x. And the centroid, where that point force acts, is right in the middle. And so over here, I'm going to apply a downward force of 490.5 x. Well, we just know, so we know that the centroid is right in the middle. Okay, and then since we're calling this point here x equals 0, and we know that this is right in the middle, we know the distance between the end and here has to be x over t. So I'm just going to write that down now. From the left to the centroid is x over 2. And from the left to the right is x. And now we can write Newton's second law. So Newton's second law says a downward force of 490.5x as a vector that's 0, negative 490.5x plus t0 plus 0, negative v is equal to zeros. And so that says that the internal tension is 0. The internal shear force, V, is negative 490.5x. And now we'll go to the moment equation about the z-axis. Does that force of 490.5x produce a moment? It does. It's, our about point is here. So if you think of that as like a hinge, this downward force would make it this way. So the moment produced by the weight there has a moment arm of x over 2. A force magnitude of 490.5x. And then would that produce a positive or negative? Yeah, that would make it rotate clockwise, so that's negative. And then you add the m, just like always. Minus vx is equal to 0. Those two terms are always there. And you get that m is equal to, that's positive 245.25 x squared plus vx, which is minus 490.5 x times x. So m, don't close.
Oh, no. I saw it.
I closed it? I did that? I know.
No, don't go.
I know. I was too. Ooh, recover, yes. Yeah. Otherwise, I have to start again because I don't remember what I wrote. Yeah. Okay, I'm saving it right now. Well, okay, so I'll go back to this. So this is Newton's second law. So we have the force of 0, negative 490.5x plus t0 plus 0, negative v is equal to zeros. So we get that internal tension is 0. Internal shear force is negative 490.5x. And then the moment equation about the z-axis, we have negative x over 2 times 490.5x plus m minus vx is equal to 0. So m is equal to positive 245.25 x squared minus 490.5 x times x. That's the v times x. And you get that m is equal to negative 245.25 x squared. Yeah.
How do you get that established on the Z-axis?
Yes. Right. So we were just talking about this at office hours today. So the way to think about that is the axis of rotation is always like if you imagine these things as pin joints, okay? The axis of rotation is parallel to the pin itself. Okay, so if you, ooh, this is like, well, that's not.
That's what you're saying. So that axis
Yeah.
of rotation is basically along there.
Yeah. So if this is rotating like this, the pin that it would be rotating around is like this. And so now if that's parallel to the x-axis, that's an x, those are x moments. If that's parallel to, the z-axis, those are z moments.
Okay.
So in this case, when we were talking about the z rotations, we're talking about hinges or pin joints where the pins are like this. And so the thing rotates in the plane. When we're talking about the x moments, we're talking about a hinge like this, which means the beam spinning like this, like a roll.
Okay, thank you.
Sure. So yeah, think about the pin that it's rotating around extending, and then just think about what axis that's parallel to. And then the last one we have to do is rotational Newton's second law about the x-axis. Nothing's going on in this problem about the x-axis. So what's producing torque about the x-axis? None of the external things are. The only thing that is that internal torque T. So we just have that torque is equal to 0. So torque is equal to 0. Right. Yeah, and the other, the way that like in statics, you're used to things rotating in the plane. If you're doing a plane problem in the XY plane, that's a Z rotation. In this case, it's 0, yeah. So functions are, the internal tension is 0 the whole way. The shear force, well, let's actually graph these. So the tension as a function of x is just 0. The shear force is a function of x. Starts out at 0 and is linear with a negative slope down to a value of negative 981. So if this is negative 981 newtons, the shear force is like this. Bending moment starts out at a value of 0, and then it's a quadratic function, concave down, with a maximum value of 981, I think, again, negative. So it's like this. That's supposed to be quadratic. And then the torque, there was nothing going on. So that graph is 0 the whole way. All right, so if this beam was a single, like had a single cross section the whole way along the beam, and was made out of a single material the whole way along the beam, and you were asked to figure out where this thing is at risk of breaking, what would you say based on those answers? Yeah, the right end is where you're concerned because there's no distinction for any of these points in terms of tension or torque. But the biggest absolute value of shear force and bending moment both occur at the right end, right at that connection between the beam and the wall. And so if you were trying to figure out where you needed to reinforce things or, use a stronger material or something, you would want to analyze what's happening right at that connection with the wall.
Yep.
Yep.
This is on the right hand. I noticed because the slope is going to the right, or because the graph.
Well, just looking at the values, we're just looking for the absolute values.
Yeah.
Like, where are the absolute values biggest of shear force and bending moment?
Oh,
because the other ones are the other two are the same.
Yeah.
And so they're both decreasing functions the whole way. So the biggest absolute value is all the way at the right end.
Right. Okay. Because we have like 981.
Right. Yep.
If it wasn't, it was like this.
Yep. Yeah, we'll see functions like that too. All right. Now there are 6 checks that you can do to make sure that give you a chance to sort of catch mistakes that you've made, because there's a lot of places where it's easy to make mistakes on these. So 6 checks that you should get in the habit of making on your internal load calculations. Yep.
Obviously, if you're pushing down on that,
well, these internal load calculations don't have anything to do with the cross section. That doesn't come into it at all. Where that does come into it is when you go from internal loads to stresses, and I'll try to bring that out when we first start doing stresses. You'll see that for the first time, we'll have to have information about what that cross-sectional shape looks like. But for now, whether this is a C shape or some crazy thing or just a rectangle or a circle, internal load calculations are all the same. We also haven't taken any materials into account. So these internal loads are true for steel or wood or whatever. For the stresses? Well, so the effect of the material is going to come in again as that relationship between stress and strain. So we're going to figure out how to calculate the stress based on the cross section. And then once you have the stress, you'll use the Young's modulus and Poisson's ratio for a specific material to figure out how much the beam's deformed. And the idea is, well, forget that. Yes, that's enough. 6 checks on internal load calculations. First, at each point, the derivative of the bending moment with respect to x has to be equal to the shear force. At each point, the derivative of the shear force with respect to x is equal to the negative of the distributed load function. And I think what I'm going to do, I'll write out these 6, and then we'll go back to the example and I'll show you how to do all of these. This is the distributed load function. And then the remaining four all have to do with endpoints only. So first, at any endpoint, so first of all, the tension is equal to 0 if and only if. Have you seen this symbol before? That's like, they use that in math. If and only if, okay, so go to an endpoint, either endpoint of a beam. And the question is the tension 0 at that endpoint that you chose? Well, it's 0 if and only if there are 0 horizontal point forces at that endpoint. And now 4, 5, and 6 are all going to be basically the same as this. Also at an endpoint, the shear force is equal to 0 if and only if. What do you think this is going to say? If and only if there's 0 vertical point force at that endpoint. Number 5, at an endpoint, the bending moment is equal to 0 if and only if. What do you think this will say? If and only if there's 0 point couple at that endpoint. Usually point couples only come up if you have a fixed joint at that endpoint. They can come up other ways, but that's the most common way. So 0 point couple at endpoint. And then the last one, at a chosen endpoint, the torque is equal to 0 if and only if. What do you think this one says? That's right. There's 0 point torque at that endpoint. You sort of probably, for number 5 and 6, it's a little unnecessary for me to say point couples and point torques because we're not talking about distributed torques and distributed couples, although it is possible that you could have those, I suppose. Okay, so let's use the last example and go through these 6 and just do it as a check, and hopefully that'll sort of point out how this works. So first, at every point, dm dx has to be equal to v. We'll go up to the bending moment function. M is negative 245.25 x squared. So dm dx is equal to negative 490.5 x. And that should match v, so we'll go up to the v function, and they're the same. So that one's good. Now, dv dx has to be equal to negative q. V is negative 490.5x. dv dx is negative 490.5. Negative dv dx is 490.5. What's a function describing the distributed load for every x value? That's right. the constant distributed load. So no matter what X value you're at, the value of it is 490.5. And so those check out. That's a good question. So Q, because we almost always, in this class, always deal with distributed loads pointing down, Q is a downward distributed load. So that's where the negative comes into the relationship. If we called Q a positive distributed load, then we wouldn't have had to add that negative. That's right. But the reason we call it a downward distributed load is because that's the kind we see more often. Yep. Yeah, you could have one. You could have like a magnetic force or something. You know, that would apply a distributed load, or electrical forces, or a planet above you. Like all that stuff applies. Yeah, like the moon's gravitational pull is applying an upward distributed load on us, but it's small. So this one checks out. Okay, so now at the endpoints, T is equal to 0 if and only if there's no horizontal point forces. Are there horizontal point forces at either endpoint? Well, at this one we know there's not. At this one we don't really know because we were lazy. That reaction force could apply or yeah, we skipped that. So in our case, we can only check at the left endpoint. But there's no horizontal distributed load at the left endpoint. So at the left endpoint, T should be equal to 0. And so I have to find the T function. And T is equal to 0 along the whole beam. So that works. Yep. Yes, that's right. So this one checks out. All of these we're only going to be able to do on the left side because of our laziness problem. If we had, before we did the problem, we had calculated the external loads at that cantilever, then we could have done the checks at both endpoints. Okay, so shear force is equal to 0 if and only if there's no vertical point force at the left end. Is there a vertical point force at the left end? Ooh, this is a little trickier one. Well, yeah, so it's important that we think about it point by point. Okay. So over here, there is a distributed load at that point, but that's not the same as a point force. Okay, like at that point itself, there's no, like, how much total force is that distributed load applying right at this point? None. It needs a finite distance to apply a finite force. So there's no point force there, and that means that the shear force needs to be equal to 0 there. Okay. If we did calculate this external load, like Ryan was saying, this would be an upward force of 981 over here. So what we would see is that we should have V equals 0 here and V non-zero here. So now let's look at the V function and see if that holds. When X is equal to 0, V is 0, like we expected. And when X is equal to 2, V is non-zero, like we expected. Yeah, so if you want to do those checks, you need to do the external loads, but yeah. That's right, at the left end, X is equal to 0. Okay, so that one works. And now the couple. So the bending moment is equal to 0 at an endpoint if there's no point couple at that endpoint. There's no point coupled here, so m should be 0 for x equals 0. There is a point couple here. We didn't calculate it, but there is one. And so if we had calculated those, we would see we should have a bending moment at the right end when x is equal to 2. And so look at the bending moment function. Plug in x equals 0, you get 0 like we expected. Plug in x equals 2, you get something. And so that one checks out. And then the last one is the torque. Well, there's no torque, internal torque anywhere. There were no point torques at either end. So that said, that we should have the internal torque of 0 here and here. Our torque function was 0, so that one holds.
I have some conceptual question.
Yeah.
So I understand we don't have to, if we have like, if we're giving external load at the right side, and we start from left, and we don't have to worry about it.
Right.
But why is that? Why we don't have to?
Because when we did our cut, so look at the piece. So here's our one cut in this problem. This is good for all x values between 0 and 2, not including 0 and not including 2.
Oh, between them.
Yeah, so no matter what x is in this range, we never get all the way to the point where we have to apply those lines. So that's why. Any other questions? Okay.
There could be 1.9999.
Yes, right. That's right.